Last time we discussed a standard or a typical shear wall, as you see here in the picture. The bars that we have at the end, this is what we call here the jam bars, and the rest of the wall reinforcing here, this is what's called wall reinforcing. In this drawing here, it shows number 6 is 16 each way, which means vertical, horizontal, and each face, which means that you have 2 layers of rebars. Like what you see here in this detail, in this section, it shows the jam bars. So the jam bars give you all of these bars. This is what you call here jam bars, the vertical ones. You have a tie around it to provide confinement for the concrete at this location. Then you have the wall reinforcing. This is a plan, which means this rebars that you're looking here at, this give you like the vertical rebar, this one. And this give you the horizontal ones. We discuss here the limits by code about shear walls. We say row minimum in vertical, horizontal direction. In both directions is going to be 0.0025. And this specific for shear walls. For gravity walls is going to be a little bit less. So for shear walls, you have higher minimum reinforcement ratio needed. The maximum spacing between any two vertical rebars or horizontal rebars is going to be 18 inches. And you will need to have 2 layers or 2 curves of rebars once the shear demand is going to be going above this limit. Also, you need to provide this 90-degree standard hook or 180-degree standard hook for the wall reinforcement, the horizontal rebars in the jam area or jam section, sometimes also is called as boundary of the wall. When V sub U is going to be more than A times square root of A prime C, which means with a shear factor equals 1. We discussed this last time. We said we're going to be talking here about this hook. If you see here, this hook at the end of the wall, enlarge it a little bit. In some cases, you're allowed just to end the rebar like this. When you have the amount of shear is not really high. Once the shear demand is going above A of the concrete, multiplied by square root of A prime C, in this case, you need to hook it with either 9 degrees or 180 degrees. 180 degrees, which means the rebar is going to be coming back. It's going to be like the standard hook of 180 degrees. Now, how do you find out the shear demand? Shear demand is going to be given to you most likely, unless you're doing seismic analysis for the shear wall for the building and then determine the amount of shear demand, which is V sub U. Now, how about the capacity? Capacity is determined based on the steel reinforcing that you put there, and also about the concrete strength. If you recall, the shear factor equals to 2 for one-way shear, and it's roughly about 4 for punching shear, which is, we call it here, two-way shear. This shear factor, usually we use it, we say area of the concrete exposed to shear multiplied by square root of A prime C times a shear factor. Now, our shear factor in this case for shear walls, it is called alpha sub C. Here we go. Now, this is going to be our shear factor. And this shear factor here, it has a range. It's not equal to 2, it's not equal to 3, it's not equal to 4. It is going to have a range here. As it says here, it depends on the aspect ratio of the wall. Aspect ratio of the wall, which means wall height divided by wall length. You see here this ratio? HW divided by LW. Here is the wall length and wall height. When the wall height, the wall length is going to be less than or equal to 1.5, you go to 3. This means short walls will have higher shear factor. So here's the shear factor. It's 3 when the height is kind of smaller compared to the length. We call this also squat shear walls. The shear wall is going to be like this, and here's the base. The base is going to be at the bottom, right? This is going to be like in this case, right? Your shear factor becomes like for beams is going to be equal to 2, right? So the shear factor equals to 2 is going to be like for beams, when you have a tall shear wall, When you have a short shear wall, your shear factor is going to be growing up. It can reach all the way to 3. How about if the aspect ratio of the wall is in between? Code says you can do interpolation. So we're going to go here to the next slide just to show this factor to come back to here. Here is the aspect ratio, H wall divided by L wall, height divided by the length. And then you have this diagram with the shear factor, alpha sub C. For short shear walls, this one, the height divided by the length is going to be small, less than 1.5. You're going to have high shear factor of 3. Once it goes to above 2, which means the height, it's going to be kind of tall shear walls, your shear factor becomes here too. So this here accounts for the shear strength coming from the concrete. Understand that. And then you multiply by the sheared area. This sheared area is going to be equal to the wall thickness multiplied by the wall length. Because when I have here any shear force, it's going to be coming this way. And the area exposed to shear is going to be determined by cutting a section this way and looking down. This is going to be the wall thickness by the wall length. And of course, you need to put the whole thing here in inches. You cannot have it in feet. So you got to be careful about units. So here's the sheared area times shear factor times square root of F prime C. So, okay. How about this rho n? What is that? I'm going to say this is to account for the shear strength. Shear strength is going to be equal to the shear reinforcement ratio divided by F sub y divided by AC. Just remind you here, AS equals to what? In this equation here, AS is going to be equal to the C ratio times A sub CV. What's the definition of rho n? Rho n is going to be for the horizontal C ratio. Whatever horizontal C ratio that you have, if you multiply here by the shear area, it means that you're going to be getting AS. Because rho n equals, this rho C ratio equals AS divided by AV or ACV. So when you say here ACV multiplied by rho n is going to be equal to the steel cross-sectional area. So, okay. And then you have your definition for all of these variables. The maximum shear strength that the entire wall can take is going to be equal to 8 square root of F prime C times the cross-section area of the concrete wall. Let's see an example, because it seems very simple here. Let's see an example. It says minimum reinforcement for 16-inch thick shear wall in the horizontal direction is nearly. Now, this minimum, without having any shear demand, it means that I need to apply the 0.0025. Let me go back here and show you what I'm talking about. You see this here, minimum shear ratio? This is regardless of the amount of shear demand and the strength that you need to design for. If you have any shear wall, this can be your minimum reinforcement. So in this example, just says here minimum reinforcement for this 16-inch thick shear wall in the horizontal direction. You say, okay, let me see first. What does it mean by minimum reinforcement? This rho n is going to be how much? Your AS minimum based on this rho of 0.0025 is going to be equal to the following. You take here the minimum shear ratio times ACV. Wall thickness is going to be 16-inch. And this 12-inch because you're considering here a foot strip of the wall. Take here cross-section area 16 by 12 times 0.0025. What you need here is 0.48 square inches. And of course, it's going to be per foot. Total reinforcement that you need to put on the wall. Since I'm going to have in here a 16-inch thick wall, for sure, I'm going to have here 2 layers of reinforcing, not just one. If you remember here, for the gravity walls and for all walls, if the wall thickness is greater than 10 inches, you need to put 2 layers. So in my case here, I need to take this and split it into the 2 faces or 2 sides. So actually what I need here per face is going to be half of this, the 0.48. As it's presented here in this equation is going to be 0.24 square inch per side or per face. Now I have few options. I'm going to go back here just one slide to see the options. I have number 5 at 14, at 16, and at 6 inches, or none of the above. Of course, you'd like to start with the smallest amount of reinforcement, which is number 5 at 16 if you can, or number 5 at 14. Number 6 at 6 each face, this is going to be heavily reinforced. So I'm going to try here number 5 and see exactly how much is number 5. I like to use it. You can see here for number 5, the reinforcement for just one bar is going to be 0.31. If I take this divide by what is needed times 12, it's going to give me the proposed spacing, the needed spacing. Someone can do it differently, but let's follow this example and then I can do it differently if you like. So the spacing here, which is going to be the maximum spacing to maintain this steer ratio, is going to be 0.31, which is A sub B. I can put it here. This is going to be here A sub B divided by AS needed. So give here the maximum spacing. I did the analysis and my maximum spacing is 16.5. The options I have 16 inch and 14 inches. I can't use here 16 inch because 16 inch is going to be greater than this value and the steer ratio is going to be less than the 0.0025. So I'm going to go here with 14 inch because this is here maximum spacing, not minimum spacing. So I'm going to go here with 14 inch. Another way of doing it, I'm going to try here the available options. You can say option number 1. I have number 5 at 16 inch. How much is AS for that? I'm going to say AS equals, it's going to be 0.31 divided by, or let's say multiply by first 12 divided by 16 inch. Can someone help me with this? Yeah. Is this correct? Yeah? No? I have here number 5 at 16. Excuse me. Number 5 at 16 is the spacing of the rebars, right? How much was the wall thickness? It was 16 inch. Am I correct?
Yeah.
All right. I have here 2 layers of rebars. So what I need to say here is going to be 2 times 0.31. Correct? It's going to be all the rebars I have there. The spacing that I have here between rebars is going to be 16 inch. So I need to divide by the spacing. And the wall thickness is 16 inch. And this should be the right way of doing it. Now help. Later. Yeah, makes sense. How about number 5 at 14? So let me try here. Number 5 at 14. The rebar I have is going to be 2 rebars times 0.31 divided by wall thickness is going to be 14 inch and the spacing is the wall thickness 14 inch? 16. So wall thickness is 16 inch and the spacing is going to be 14 inch. How much is it? 28. Good, which is more than 0.0025. This give you okay. This is the one that I can use in my design. Questions? I guess this is much simpler way of doing it. You just figure out the spacing and then you compare the spacing with whatever is needed. Thank you. All right. I'm gonna go here to next slide and see the next example that I have. This example here has some forces. So the steel that I need to provide there, it needs to, number one, satisfy the minimum required. Number two, be able to resist the strength needed, the shear strength needed. The wall thickness here is gonna be 14-inch, which means I really need 2 layers. So this makes sense. Each face is good. Concrete strength 4,000 psi. Seismic shear 380. This is gonna be here V sub U. So let me put it next to it. I'm gonna say this gonna be here V sub U. The shear wall height is 16 feet and the width is 10 feet for the length. Width or length is the same. Now this is gonna be controlling here my shear factor. 16 divided by 10 is gonna be 1.6. And they say, what is the minimum reinforcement? Now, it's true that it just says here the minimum reinforcement, but you have some shear demand that you need to check the shear strength for. First, I'm trying here to find out this alpha, the shear factor. So you say here, HW divided by LW is going to be equal to 1.6. I'm going to take you back here and go to our diagram. If the aspect ratio is 1.5 or less, your shear factor is 3, it's going to be 2 or more, it's going to be 2. It's going to be in the middle, this is going to be the equation that you can use to do the interpolation. It says 6 minus 2 times the aspect ratio. It's okay. Let me move there and see how I can use this. 6 minus 2 times the aspect ratio. Here's my equation. Because my value here is lying between 1.5 and 2. It's actually 1.6. Aspect ratio, 1.6, 16 divided by 10. And with that, my shear factor equals 2.8. Now I can rewrite my equation. My equation is going to be phi-Vn. This is going to be here the shear strength. The phi factor first is going to be equal to 0.6 for shear walls. Keep this in mind, it's not 0.05. So for shear walls, the phi factor, please write a note about this, is equal to 0.6. The equation here becomes phi times ACV, area exposed to shear. This when you cut a section through the wall, then you look in the plan view. Your alpha sub C here is 2.8. F prime C is 4,000. Rho is going to be the shear ratio that I don't know because I have here a few options. Times Fy. Again, strength factor is 0.6. I'm done with that. Cross-section area. The wall length here is 10 feet. So you say this is going to be here the wall length. You multiply by 12 to give you the wall length. So this here is going to be L sub W. Wall length, entire wall length. Wall thickness, as you see here, is going to be 14-inch. So I can say here, this is going to be wall thickness. 14-inch. Everything here needs to be in inches. Times. This alpha sub C, we say is going to be 2.8. Square root of prime C is going to be 4,000. You divide this by 1,000 to get your answer in kips. And then you say times rho sub N times F sub Y, which is 60 psi. Now, in this equation here, I'm setting V sub U equals to phi Vn. I put this demand is going to be equal to the capacity. And for that, I'm going to have here one unknown, which means this is going to be rho N needed. So I can say this is going to be needed shear ratio. In this equation, once you set phi Vn, which is the capacity equals to your demand, the 380 that was given, you can just solve here for rho sub N. Equation is cleaned up a little bit. and here is row sub n. The good thing about this method that by doing this, I can confirm which one controls. Is it the row minimum or the row needed? If you like to try the options available for each one of them, you need to find out row sub n and then compare it with 0.03, right? And compare it also with a 0.0025. So this can be a kind of a simpler way that's shown here in this example. And your row n needed is going to be 0.03. Your minimum is 0.025. And so this is going to be the one that controls your design. This is what you need here to use. So let's see how I can use this. The AS needed is going to be equal to the steel ratio multiplied by the cross-section area of the wall. Wall thickness is 12 inch. I'm going to be taking here just a foot of the wall. So this is going to be like 12 inches. I'm going to say 12 inches strip of 12 inches. With that, I'm going to have what is needed as a steel in both sides of the wall per foot. So you take the 0.033. This is what you need to add there to satisfy the minimum and the strength times 14 wall thickness times 12 inch for a strip. This is what you need, 0.554 for both sides. For each side, or for each face, this is what you need. This is going to be 1/2 of the 0.554. I'm going to pick here number 5. Why do I pick number 5? Look at all the rebars provided. Number 5, number 5. I'd like to stick here with number 5. Someone's going to say, how about number 6? I'm going to say, which one here would give you less reinforcing? And it's going to be safer in terms of materials. You're going to say number 5 at 16. What's right next to it? You see maybe number 5 at 12, and then number 5, 6 at 16, then 6 at 12. So I'd like to start first with the number 5 and see if it works. I'm going to be taking here the 0.31, just one rebar, divided by what is needed in one face, multiplied by 12 inch. I have here 13.4. So what I have here, 13.4 inches. It's going to be the maximum spacing. So let me put this term here. I'm going to say maximum spacing. What is available in the options? I'm going to say what's available. I have 16 and 12 inch. So here's 16, number 5 is 16, number 5 at 12. So definitely I'm going to go here with number 5 because if I go here to 16, I'm going to have less reinforcing than needed. Questions? If no question on this subject, I'm done here for the slide set, and also I'm open for any questions on the quiz. You have any questions?
Possible to go over the midterm?
Okay. What exactly in the midterm? Tell me.
The part where it's at the number 2 on the midterm, saying how I didn't understand when they show the coordinates, but it said show no analysis. I didn't understand it.
Okay, no problem. Now, just want to confirm here. On Tuesday, what's going to happen? I guess I'm going to give you, right? I'm going to give you the formula sheet. So you'll have the formula sheet. Did I answer some of the questions here? Yes? No? Same formula sheet that we have used in midterm 2. Your question about number 2?
Yeah, what is it, advise if the column is also.
Yeah. All right. Is everyone following us? You guys know what we are talking about here? Yes? No? Like to hear from you guys. I don't hear anyone. Do you see the other screen here? Yes.
Yeah.
Yeah. All right, very good. So you have 2 cameras now.
Yeah.
So what you have is a few charts, right? And then you need to pick the correct one. You have a few of them, right? Let's say this is gonna be the right one. So I'm gonna say this is gonna be a little bit thicker, right? The factor that I have here on the y-axis says k sub n. I'm gonna say in here is gonna be k sub n equals. It's gonna be equal here to the nominal capacity divided by f prime c by a sub g, cross section area of the concrete. Is it there? Is it good? Better?
Yeah.
The load that you have is actually P sub u, not PF. In order for me to be able to mark on here, I need to sit and say P sub u equals PPN. So I'm going to sit here, P sub u equals PPN. Demand is equal to the capacity, right? I know that at this point here, the P factor is 0.65. I know that P sub u is equal to 640. I guess I can solve for this Pn. Now I have Pn. You agree? Right, good. If I have Pn, I'm going to be taking it and use it in this equation. I have a prime C, I have Ag, therefore I have K sub n for what? For the demand. Why? Because this is here about the demand. So this is going to be here my curve. K sub n, I'll find it. It's going to be about here. I'm going to say, you know what? This is going to be my K sub n for the demand. So my demand point is going to be this point. As long as it's going to be below this point, you're good. Because this is going to be here the maximum force that you can apply. You can reach Kn of this value, and according to your midterm too, that is equal to 1. Correct? If you look at the chart in your midterm one.
Oh, yeah.
So as long as you're going to be below it, you're good. This is going to be your capacity point. So what you need to do is to do this simple analysis. For me, you're not really doing analysis, you're just using the chart. So this equation is not really analysis per se, right? It's going to be just using the chart because you need to show point here. And then you mark the point and you say it's going to be problem number 2. And of course, you write the value next to it. Let's say it's going to be 0.9 or 0.8 or whatever, you just write it here. You say Kn equals. That's it. We're done.
So once you find we don't have to plug in for Kn software.
You just figure out Kn here from this equation, right? How did you do it? It says give me Pn. Where did you get Pn from? You take P sub u, your demand, you divide by the phi factor. You remember this equation?
Yeah.
Yeah. So we start here. Let's give you number 1. You're gonna put in the box. Number 1, you have Pu equals to phi Pn. It's gonna be 0.65, and we have this P sub u. You figure out Pn. You go to the Kn equation. It's gonna be number 2. You say Kn equals Pn divided by. Where did you get this equation from? From the chart. It's right there on the chart, right? So you take this Pn divided by these 2 values. And then you go in here, you pick your chart, the correct one with the same steer ratio, right? And then you put the point right here. That's it. Done. You can just do a straight line like this. If you like, you just do a dash line like this. Once it hits your curve, you're going to say, okay, good. I'm lower than this. I'm good. Because give you the maximum point was only Egce loop. So this point here is going to be within the envelope. You see here, this is going to be your envelope, right?
Yeah.
If your point is going to be here, it means that you're within this envelope.
Okay.
Yeah, you know, this is going to be Egce loop, P, and this is going to be the moment. If your point is here, you're good. We have some moment. In the problem number 2, you have no moment, right? So it's going to be only P, so you're good. As long as you're between these 2 values, you're good.
Okay. I did that. I got Kn as 0.62 and it was
Okay, all right. I'm just throwing here a number like 0.9, double value.
and then for Rn, H would be 30 from the footing.
No, this is about the column. Is this about the column or the footing?
The column.
About the column. So it's going to be H of the column, which is 20 inches.
Okay.
Right?
Yeah.
So the footing is going to have certain problems and certain questions. Column is going to have its own H and dimensions, you know.
Okay.
Right? You have more questions?
Yes. For is there a slide to find like the balance point? Is there a slide to review?
To find the balance point by analysis?
Yeah.
Yeah, absolutely. We have a very good example on this. Let me show it to you. Here's a slide set, show that you guys have seen it. The last one of the column design, right? This is Gabby slide set number 11. All right, take a note about this. Here's the balance point. How do you find it numerically or by analysis? We have this example line 5. What page? Page 8. Starts at page 8 or slide 8. Item C is giving the balanced strain condition. Okay, item C. Here's B, which is the toughest, and here is C, balanced condition. Start at slide number 16. And it ends right here on 18. So there's going to be actually 2 slides and 2 slides in the fraction. So just 2 slides. It's so simple when it comes to analysis. You shouldn't miss it. This is going to come again in your quiz. You're going to have the balance point. You better know how to do it. Yeah. All right. Any other questions? Yeah.
For the footing moment, equation, I know it's QB squared root of 2.
Yeah.
But I was confused on how to find x. I know in the slides it shows, but one of the values I was find.
Questions. Right. Happy that you have your questions ready. This is very good. Yeah, certainly. Yeah. I mean, at least you start to think about it, right? When you're studying. If you like to find out x to determine the maximum moment, x is going to be here. It's going to be this. So you have the total footing length, subtract the column, width, divide by 2. You don't need an equation, right? Just throw any numbers. I'm going to say this is here 8 feet. This column is a foot. How much is to the right? How much is the left? You can say 8 minus 1 is how much? 7. You have 3.5, 3.5. So it's going to be 3.5 feet, 3.5 feet. Just come up with any numbers. Okay?
Professor,
Yeah, go ahead.
can you move the camera? I can't see.
Which one? We have 2 cameras, right? You see here that we have 2 cameras. Are you aware of that?
Oh, there you go. Sorry.
Okay. So it's going to be the top one.
Yeah.
Kind of lighter.
Thank you.
No problem. Yeah. You have more questions?
The tensile strength would be the EMN, which is like,
Tensile strength. It's about tension only.
oh,
From the name of it, it's going to be tension, right? Like tensile strength.
okay.
So where is this point? This point is going to be when you have pure tension.
Oh,
Do we have equation for it? Yeah, and the equation is simple. You can say phi Tn equals the phi factor, the 0.9 as times Fy. That's it.
compression to EMN, EPN.
Phi Tn is going to be tensile strength. The interaction diagram is going to be this point here. Yeah. We're good? All right. So what's going to happen on Tuesday? We're going to start with the quiz. I guess you guys are done with all your submittals by now. Everything is submitted. This coming Tuesday, before you come to the class, I'd expect that you should have uploaded all the submittals. So I'm going to post here something. It's going to be the final submittal. In the final submittal, you submit all the files all in one shot, reviewed, cleaned, corrected, right? If you feel that you have done any mistakes, right, you just upload it. And what's going to happen on Tuesday, I'm going to start by reviewing one by one. I'm going to ask you to come by. I'm going to be reviewing your project with you and assign your grade for the project, while the rest is taking the quiz. We're good? Any questions on the quiz? Any questions on the review? Yes, Danny, do you want to say anything?
So like, we're doing the quiz, right? And then you want us to come up mid-quiz to review our project submittals?
Right. So we can have the quiz, let's say, for 30 minutes, right?
Yeah,
So I'm going to give you the entire class time. It's going to be hour and quarter. So actually what you need, if you're solving it, is only 30 minutes, right? Meanwhile, you start here to take the quiz. I'm going to ask one by one to come by. We can open his files in 5 minutes, review it with him. With each person. Does it make sense, Danny? Or
yeah, sounds good. I just like,
yeah. So there's going to
yeah.
be a quick discussion. I'm going to ask you a couple of questions if you're okay and everything is good. And I'm not expecting to finish on Tuesday. So the review is going to be taking place on Tuesday and Thursday. But we have many people. So I want to be sure that I don't get squeezed on Thursday, right? Especially on the Thursday, I'm going to have the final review. And I'm sure that you'll have questions. Any comments, Danny?
Understood, Professor.
Right, thank you. But if you have any questions, let me know. All right, if no questions, I'll see you Tuesday. Please go ahead and sign off. Put your name in the chat room and you can leave.